How much work is required to make a car that has a mass of 4,000 kilograms move from rest? So from rest means that the initial velocity is zero. If the initial velocity is zero, if you've got no velocity, you've got no kinetic energy. So the initial kinetic energy is zero. You're going to speed up to a velocity of 25 meters per second. That means you're going to have kinetic energy. Work is going to be done to give you kinetic energy from no kinetic energy. We know work is force times displacement, but it's also change of energy. Here, change of kinetic energy, final minus initial. The final kinetic energy is 1/2 mv squared, 1/2 times 4,000 times 25 squared minus 0 because the initial was 0. So we would take 1/2 of 4,000, which is 2,000, and multiply that by 25 squared. Run this through my calculator. We'll get an answer in joules because the unit of work is joules. We got 1,250,000, I'm sorry, 1,250,000 joules. How much work is required to stop a 1,200 kilogram car traveling at 15 meters per second? If you're stopping a car, the final kinetic energy is zero because the final velocity is zero. How much work is required? Well, if you're removing all of the energy, that's the change of energy. So let's find out how much energy it had when it was moving. That's the initial velocity because it's coming to a stop. The final velocity is zero. So final minus initial will have zero minus the initial kinetic energy. Work is a change of energy, change of kinetic energy. The final is zero, so zero minus, and then we calculate the initial by 1/2 mv squared, or 1/2 of 1,200 times 15 squared. 1/2 of 1,200 is 600, so 600 times 15 squared. This will be a negative number because we have 0 minus this value. And the work should be negative if it's causing the car to come to a stop. If you put the force in the same direction as the car, it will speed up. The force must be opposing the direction of the car, and that's why it's slowing down to a stop. Our answer was negative 135,000 joules. All right, a baseball mass 140 grams. Let's convert this to kilograms. So we're going to divide by 1,000, 0.14 kilograms. It's initially traveling at 32 meters per second. It hits a fielder's glove at a distance of 25 centimeters, or 0.25 meters. When the ball is caught, when it's caught, it's no longer moving. So the final velocity is zero. What's the average force exerted on the glove by the ball? Well, we know work is force times displacement. We also know work is a change of energy. Here, the ball is going from some positive velocity to zero, so that's a change of kinetic energy. And we can set that equal to force times displacement. If change in energy is work and force times displacement is work, then force times displacement is a change of energy. Final kinetic energy minus initial, where 0 minus initial is equal to force times displacement. Initial is calculated as 1/2 mv squared is equal to force times displacement. I'm keeping the 0 minus in just to remind ourselves that the work will be negative on the change of energy side. And also the force and the displacement are in opposite directions. So if the displacement is positive, the force has to be negative. Plug in our numbers. On the left side, we have negative 71.68, and on the right, we have force times 0.25. Divide both sides by 0.25. And the force that we get will be based on negative 71.68 divided by 0.25. And we got negative 286.72 newtons as our force. In which of the following situations is zero net work done? Net work would be based on the net force, so we're looking for something where the net force is zero. Net force is zero when there's a constant velocity, zero acceleration, balanced forces, equilibrium. We can see in answer choice D, a box is pulled across a rough floor at constant velocity. So the pulling force must match the force of friction. Net force is 0. So it's 0 times any displacement, still 0. Initially, a body moves in one direction and has a kinetic energy of k. Then it moves in the opposite direction with 3 times the speed. Here I'm just going to do like 3 arrows to the left to indicate 3 times as fast, but in the opposite direction. So it's 3 times the velocity. We know in our formula, the velocity is squared. 1/2 mv squared, we end up with 9 times the kinetic energy. Because it's squared, the change in direction doesn't matter. The work expended to accelerate a car from 0 to 30 meters per second. Looks like they want to compare 30 meters from 0 to 30 and then compare that to 30 to 60. And you're tempted to say it's the exact same because you're only increasing by 30 for each. But let's actually look at it, and let's pretend like the mass of the car is 1 kilogram. It's just a placeholder. So if we're going from 0 to 30, the final kinetic energy would be 1/2 mv squared, or 1/2 times 1 times 30 squared. The initial kinetic energy is 0 because you're starting at 0. And we're just going to calculate the change of energy based on going from 0 to 30. So 1/2 of 1 times 30 squared, we get 450 joules. That's how much energy it takes, or that's the change of energy, to go from 0 to 30. What about from 30 to 60? Well, 60 meters per second will be our final velocity, 30 will be our initial. So we're going to calculate kinetic energy for 60, and then we're going to subtract the kinetic energy from 30. Keep in mind the velocities are squared. Now we've already done the kinetic energy for 30 on the previous problem, that's 450. So let's get the value for the kinetic energy for 60 and then subtract that 450. 1/2 times 1 times 60 squared. When we do this, we get, was that 1800 minus 450? So 1350 joules. So it takes a lot more energy to go from 30 to 60 than it does from 0 to 30. Let's go through the answer choices. We're looking to find that 30 to 60 is greater, is less than required to accelerate from 30 to 60. And just I like to mark off the part of the multiple choice that makes that multiple choice wrong. Number 7, a bullet with mass of 12 grams. That means the mass is 0.012 kilograms. 0.012 kilograms. Strikes a fixed block of wood and penetrates a distance of 5.2 centimeters. So the displacement would be 0.052. The final velocity is going to be 0 because it embeds into the wood. The speed of the bullet just before the collision is 640 meters per second. The average force that the wood exerted on the bullet was. Again, this is another one where our kinetic energy is going from some value to 0 because it's coming to a stop, so we have a change of kinetic energy. Final minus initial. And we're going to set that equal to force times displacement because both of those, or either of those, are equal to work. So final kinetic energy minus initial. Final kinetic energy is 0 because it comes to a stop. And then initial is calculated as 1/2 mv squared is equal to force times displacement. Let's put in our numbers. 1/2 times the mass of 0.012 times the velocity squared. The velocity is 640. Don't forget to square it, is equal to force times displacement. Displacement is 0.052. With our calculator, we'll take half of 0.012 and then we'll multiply that by 640 squared. Once we have a value, we'll divide both sides by 0.052 and our equation will be solved for the force. Looks like I did drop that negative, which the force, it would be in a negative direction. None of our answer choices are indicating that negative direction, so it's probably just looking for magnitude. Their answer in scientific notation for A matches my answer, 4.7 times 10 to the fourth. Again, it looks like they were just looking for magnitude. If this was free response, we'd probably want to indicate that it's in that negative direction since the displacement was positive. But either way, we can tell answer choice A works. How much energy is dissipated in braking a 1,000-kilogram car to a stop from initial speed of 20 meters per second? Here our final kinetic energy is 0 because the velocity is 0. And then how much energy is dissipated? This is work done by the force of friction. Friction is what's going to slow down a car to a stop. So what we're going to do is we're going to find out how much energy is dissipated. Well, how much energy do you have? If you've got 5,000 kilograms of kinetic energy and you come to a stop and you have 0, well, that's how much energy was dissipated. So let's find out how much kinetic energy we have, and that's how much is going to be dissipated because it's going to go to 0. 1/2 mv squared, or 1/2 times 1,000 times 20 squared. That's equal to 200,000 joules. And that 200,000 joules is going to 0. So that's how much was dissipated. We dissipated all of it. Answer choice B. In which of the following situations is there an increase in kinetic energy? Well, if you increase your height, you're generally going to be slowing down. If you're at constant speed, you're not increasing kinetic energy. C says you're going faster. That's kind of good. Going around a fixed altitude or constant speed, those don't mean you're getting more kinetic energy. To be fair, this is rotational kinetic energy. We'll get into that in the spring. But when you see something moving faster, that is kinetic energy, still an increase in kinetic energy. Number 10, if you were to double the speed of an object, the kinetic energy is, well, if we put everything in as ones, 1 times 1 times 1 squared, and we're doubling the speed, that last 1 becomes a 2, and it's squared, so that's 4. It's quadrupled. Number 11, an elevator supported by a single cable descends a shaft at a constant speed. We know constant speed means balanced forces, no acceleration, net force 0, equilibrium. More importantly here, balanced forces. The only forces acting on the elevator are the tension in the cable going up and the gravitational force going down. Which of the following statements is true? The net work by the two forces is 0 joules. E. That's the right answer because the net force is 0. If the net force is 0, that net force times any displacement would be 0. So the net work done by the two forces is 0.